Okay, good.
Okay. All right. So welcome everyone. In the middle of the great season, including the NeurIPS season.
Yeah.
We're so lucky to have with us Jeff Shainline today, right? Visiting us. In fact, you were also at NeurIPS here.
Yeah. Absolutely.
So welcome to the INC Chalk Talk series. Always excited to have a great attendance here, people here. And so today is a bit unusual. We haven't had superconducting AI yet, but today we'll hear about really great, exciting work pushing the envelope of energy efficiency and literally coolness of AI systems, right? At what temperatures?
4 Kelvin.
4 Kelvin. So really, really cool.
That's pretty balmy compared to something.
So Jeff has been, many years has been a distinguished scientist, has been at NIST for over 12 years, who has been leading several programs. Recently also your PK's fellow and all that, right? So great work in the field. And recently you started the company called Great Sky. And
Yes.
so you'll tell us about all the great science and all the excitement that is happening there. So Jeff, please.
All right, thank you. Thank you very much. Really appreciate you accommodating me here. And yeah, so like Gert said, I was at NIST for 12 years, started developing this technology, and recently left actually. So a year ago, I left NIST altogether, started this company, raised some money, and now we're trying to build this technology and sort of make it real. So I wanted to speak to this audience because we're looking for some computational neuroscientists to help build this. Okay, so what are we talking about? Maybe it's probably best if I don't use this laser pointer and actually just use the on-screen laser pointer so everybody can see it on Zoom. So yeah, this talk is about building neuromorphic computing hardware using superconducting computational circuitry with light for communication. And we think this combination allows to scale up to very large cognitive systems. And I'll say more about what that means. So in this talk, I'm going to describe the basic concept, the motivation for why we're trying to do it this way, some of the experimental results, and then the modeling framework. I'll try to spend most of the time on our modeling framework so that computational neuroscientists can get a tangible sense of what it would take to design circuits and networks in this hardware. So first, this is sort of maybe preaching to the choir here, but I'm going to just make sure we're all on the same page by defining the contrast between two approaches. So on the one hand, you have the conventional approach, digital computing, represent everything in binary digits. You separate processing and memory, so you have a von Neumann architecture with compute over here and memory over here, and you're shuffling bits between. And then you usually communicate everything around with a shared switching network, some routing network that sends packets of information. By contrast, when we're thinking about the brain, everything is analog. Spikes may be binary, but all the computations are analog in the sense that information is represented as a continuously varying membrane potential. And processing and memory are integrated. Synaptic weights store the memory, but they are accessed as information comes in. And so there's not a separate call to memory operation. And for us, quite importantly, communication is over direct, dedicated axonal connections, which leads to the avoiding communication bottlenecks related to high traffic on that routing infrastructure. So what we're trying to do is basically capture all of this as much as possible, maybe sometimes even more than is in the brain in artificial hardware so that we can scale up to very large systems with low latency and extreme energy efficiency. Okay, so the way we think makes sense to do this is to build superconducting optoelectronic neurons. And what that means is that we use superconducting circuits to do all the computation. That means synaptic processing, storage of synaptic weights, dendritic coincidence detection, all the learning rules. They're all implemented with superconducting circuits based on Josephson junctions. And we use Josephson junctions. Josephson junctions are the most ubiquitous superconducting circuit element. What a transistor is to semiconductors, a Josephson junction is to superconductors. And we choose those circuits for two reasons that I'll highlight. One is that JJs, as I'll probably refer to them, have the highest speed over energy quotient of any known circuit element, which means there's no known way to compute faster with less energy. That's pretty compelling. Another reason is that they naturally implement the operations that we care about for neuromorphic intelligence. For example, two JJs wired in parallel naturally can sum many inputs. They can perform a rectified linear unit or a sigmoid-like transfer function, and you can store synaptic weights in a high bit depth memory right there in the same material layers, the same fabrication layers as all the computational circuitry. So those concepts make us think that superconducting circuits based on Josephson junctions are a good match to brain-inspired intelligence. However, there's still this shortcoming that superconductors are still not excellent at sending their information to many thousands of destinations as we would like them to do for neural scale connectivity. And so we use light for communication. So we build these neurons that every single one of them has its own light source, transmitter circuitry, and dedicated waveguide. So when the neuron is summing inputs, it reaches a threshold, it produces a pulse of light generated by a semiconductor light source that's coupled to a photonic waveguide. That waveguide branches out to many thousands of destinations, and at every recipient synapse, what I'm showing here is a superconducting single photon detector. This means we are sending information between neurons to thousands of synapses or overcoming this fan out limitation. We do it at the speed of light, the fastest velocity in the universe, very important for low latency across large systems, and at the lowest possible energy of order 1 photon per communication event. This seems promising, so let's go for it. These are the basic concepts that led to this whole direction of superconducting optoelectronic neurons and superconducting optoelectronic networks. So we do approach some physical limits like light speed communication, single photon energy levels, and then, as I said, Josephson junctions with this high speed over energy quotient. They can actually approach the Heisenberg uncertainty limit delta E, delta T. So we get to some of these fundamental limits of communication and computation. It's sort of summarized here in this slide. I'll just really drive home the point here on the architecture that we think the secret to overcoming some of the scaling limitations of conventional AI is to physically instantiate the network and hardware. This is not a secret. Gert's been doing this for decades. He knows that if you want to make the smartest systems, you build the network into the hardware as opposed to digitally emulating it. And so that's at the core of everything we're doing. I've described the computation and the communication. I'll say a little bit more about memory. And then the final point is that when you put this all together, it leads to this very scalable computing technology that we think has its own potential for an exponential scaling trend. We know about Moore's law, where you gradually shrink transistors and therefore you can double the amount of compute per unit in constant unit time. This is different. This is doubling the amount of compute in every new product generation by bringing more infrastructure into the system without being plagued by communication bottlenecks or energy barriers that limit your ability to scale. So we think there's a new exponential scaling trend that's enabled by building brain-like hardware based on superconductors and light. Okay, so now what I'm going to do is I'm going to walk through this cartoon picture of a neuron and just highlight a few of our experimental results that indicate that this is physically tractable. I'll start with a synapse. So in our hardware, a synapse looks like this. It's a superconducting single photon detector that I've drawn as a variable resistor in series with an inductor. This is a superconducting path to ground until a photon hits it, and then it becomes highly resistive and kicks all the current into this branch of the circuit, which then gets coupled into the post-synaptic part of the cell, which we think of as a dendrite. And it's this two Josephson junction circuit that I mentioned before. A JJ is shown as an X here. So this is a 2JJ circuit. So it's a single photon detector with two Josephson junctions. And when this gets driven to activity by a photon detection event, current is added to this integration loop. The synaptic weight is established by there's a few different ways you can do it here. I'm drawing it as this synaptic bias current that determines how much current gets added to that loop every time a photon is detected. So you can think of this as the the current on the postsynaptic or the charge on the postsynaptic membrane. When you work with superconductors, it's the dual of everything. So charge goes to current. So we store current in these integrating loops, and that's our sort of analogous to the membrane potential. So here's an example of a train of single photon events coming in. And you can see we can change the synaptic weight and perform integration. So this is a synapse where we're putting in a train of 20 pulses. And we see that with a really low synaptic weight, you have to integrate a number of pulses before you get an appreciable signal. And you can ramp that up to a large synaptic weight where just a few incoming events drive it to saturation. We can encode information in a number of formats like burst coding, where the information is encoded in the number of pulses that were in a train, or frequency coding, where the amplitude of the postsynaptic signal gets larger if the pulses come in rapidly versus slowly. This is kind of bread and butter frequency coding type of behavior. And this is all done with the same synapse. And then another thing that I'll emphasize is that time constants matter a lot. We are doing some research around exactly how we can leverage this, but in the brain, we have sort of the fast versus slow receptors where you might have a few millisecond time constant for the AMPA the receptors, or maybe 100 milliseconds for the slower glutamate receptors. And we think that's important to being able to integrate signals on different timescales. What we have with this hardware is the ability to go very fast. We show 200 some nanoseconds here. We can actually go even faster than that. We're working with few nanosecond time constants right now, all the way out to milliseconds. And this isn't even the longest you can go, because the superconducting postsynaptic signal has no dissipation. The superconducting current doesn't dissipate. You can store things indefinitely. We've actually shown up to 48 hours with no degradation whatsoever. So you can have time constants spanning this range of of scales here, and we think that's very important to the ability to integrate information across time scales and have memory on everything from the interspike interval all the way to the life of the organism. By organism here, I mean some massive superconducting brain that will build one day. Yes.
I have a one question. You know that the photons arrive with difference in the medium, that they have some specific impedance, and then they have different impedance inside of the superconductor. And then when they arrive, the photons, there are some reflections. And then the reflection is the difference between the impedance. And then you made the calculation about the difference of the impedance between.
Yeah, so the way you're describing it sounds more like a microwave circuit. So you have a photon traveling through a transmission line and it gets coupled into some detector with an impedance, and you're going to have a reflection coefficient. In our case, we're actually talking about optical photons, telecom wavelengths. They're in dielectric waveguides made out of silicon nitride, for example. And then these detectors that I'm talking about, they're actually just little absorbing materials. And so we've shown that actually the group we were in at NIST kind of led the world in this. I wasn't involved in the project, but other people there showed you can get 98% detection efficiency in these detectors with almost no reflection. So it's not quite as challenging as impedance matching in a microwave circuit going into a detector. It's just an absorbing material that when the superconducting wire absorbs the photon, it gets hot, breaks superconductivity, and becomes very high impedance at that moment. But you don't have to worry about reflections coming off of it. You can get less than 2% reflection. Make sense? Yeah. You'll take my word for it.
Don't mind.
Yeah, go for it.
So you have the inductors in the circuit diagram and resistances, right? And so our immediate reaction is when you have resistances, you get Ohm's law, you get dissipation.
Yeah.
Right? But I guess those are superconducting resistance, they're 0 ohms.
Well, in this branch, so in this branch of the circuit, when it's biased in the steady state, current is flowing directly through the so this variable resistor switches from exactly 0 resistance to like a kilo ohm. And when it's in the 0 resistance state, it's not dissipating power. But you do dissipate power every time you detect a photon, and then you have to rebias it again, half Li squared. So it's not free, but the energy that you spend rebiasing all the single photon detectors is still pretty small compared to the energy you spend making the photons in the first place. That ends up dominating all of our power consumption.
They're still much better than a standard fully detector.
Yeah, you don't have leakage current or anything like that. Yeah.
And that transformation, from the leakage to non-leakage is very fast. You can regenerate very quickly.
The time to rebias the single photon detector is about 10 nanoseconds. So that sets what we call our gamma oscillation frequency of 100 megahertz. So with this hardware, the way we usually, our rule of thumb is everything's accelerated by 1 million relative to the brain. Gamma oscillations are usually 30 to 80 hertz, call it up to 100 hertz. We go to 100 megahertz. But that persists all the way up to some system that would be the size of that supercomputer I saw up there. Even if that entire thing was made of this, gamma oscillations at 100 megahertz. There's no scale dependent latency until your propagation is limited by the finite propagation velocity of light, which ends up being something like 30-meter wide systems. And that can fit more than 100 quadrillion parameters in it, like a very large model. So that's what we want to build. Okay, so then the next question is, how do you change the synaptic weight? How do you store the synaptic weight locally there with the single photon detector? It's this circuit. So I won't bother you with all the details, but the basic idea is that you can program in the amount of current in this loop here. It can go either direction, either strengthening or weakening the synaptic weight, potentiating or depressing. And that just couples into the same single photon detector synapse that I was showing before. So now you have the single photon path coming in over here and the synaptic weight coming in, converging on the same two Josephson junction circuit element. Now we added four more Josephson junctions to do the plasticity. And we can do things like this. So this is measured data where we're putting in these dashed lines are synapse events, single photon inputs to our single photon synapse. And then we put in potentiating pulses between those. So we can ratchet up the synaptic weight, and then it'll stay there if we don't put in any more pulses in between, and then we can ratchet it back down. So this is a 3-bit synapse here, about 16 discrete levels, sorry, 8 discrete levels. And this is used basically just for the illustration purpose because you can clearly see it changing between each of those. But we've done more. We've shown up to 8-bit. Actually, this is a little more than 8-bit, about 400 levels. And the same thing, you can put in these programming pulses and you get really fine gradation between these synaptic levels. 8-bit's not a limit. It's just the penalty you pay for going beyond that is that the circuit gets kind of large because this inductor that's storing the current there spatially becomes a little bit large. But we think somewhere between well, a lot of the world, like DeepSeek, has this 1.5-bit model. So there's a lot of momentum going to lower bit depth, but we think up to like 4 to 8 bits seems to be the comfort zone here. And these have been programmed sort of in a supervised manner where there's an external control signal. You just put in pulses and that changes the synaptic weight. Where we really want to go with this is local learning rules, where synaptic activity in the circuit is all that you need to train it. And we're really in particular interested in excitatory 3-factor learning rules, like has been pioneered by Wolfram Gerstner, coupled with inhibitory sort of balancing rules to achieve excitation inhibition balance. These can also be programmed really fast, sort of on the fly. You don't need to take the synapse offline. So what we're showing here is there's just a constant train of synapse events coming in, and and the green means potentiating pulse, the red means the depressing pulse, and we can strengthen or weaken the synaptic weight on the fly as the synapse is operating. And it ends up being the time limit is about 10 picoseconds for those programming pulses, although these were slightly longer in this experiment here. Okay, so then the next thing I'll talk about is dendrites. My personal philosophy is that one of the major things that's missing from AI is complex neurons with dendritic trees, because Maybe some of you have seen the work where they've shown a pyramidal neuron in a I think a human brain, although it might have been a mouse. In order to model its transfer function, you need a deep neural network of anywhere from 2 to 8 layers in depth just to model one pyramidal neuron. And so we think if you build, instead of going beyond the point neuron model to elaborate dendritic trees, that you're going to get a lot more computational power per parameter. And we haven't shown all of that yet, but what we've shown is here's a 2 synapse to 1 dendrite circuit. So this is a coincidence detector. And the x-axis here is the delay between the arrival times of those 2 synapses. And what we show is that the post-synaptic signal, the membrane potential on the dendrite, if you will, is a sharp function of the delay between those two arrival events. And you can change both the amplitude of that with changing the synaptic weight. In this case, the synaptic weights were the same for both of them. And you can also change the width with the time constant of decay of each of these synapses. And that can be done, as I was describing, across a wide range of values. So you can be doing coincidence detection on a 10 nanosecond time scale and just looking for really fast gamma oscillation correlations, or on a much longer time scale and use something similar for like a Hebbian type spike timing based learning rule. Another thing that we showed with the same 2 synapse to 1 dendrite circuit is inhibition. So now imagine one of these synapses has the opposite sign of coupling. So there's a train of pulses coming into the first synapse, and then there's one pulse coming into the second synapse, the inhibitory synapse, and that depresses the behavior so it basically removes the excitatory synapse from contributing to the dendritic membrane potential. And then as the signal in that inhibitory dendrite or inhibitory synapse decays, then the response of the excitatory synapse ramps back up. So this is what you'd like from inhibition, and it's straightforward to implement with these circuits. Let's see. Then I'll just briefly say a little bit about the routing, the photonics. So one of the nice things about photonic routing is it's passive. So you generate a pulse of light. That is an active process. But then you can couple it into these passive waveguides. They don't need to be biased. They don't need anything. They're just dielectrics made out of usually silicon or silicon nitride. And you can do this passive fan out in multiple planes. So what we're showing here is light coming into this middle waveguide, and then it passively couples up and down to the upper and lower planes, and then it branches out laterally. And this allows you to passively fan out to many destinations. And so we've shown both 2 and 3 planes of waveguides. Do I need to do a dance of some kind? Oh, it's better? Okay. As long as it doesn't turn it into nap time, then. So yeah, here we do this tap and transition thing where light will be coming down this waveguide. You tap off the certain amount that you need to route somewhere else and transition up to another plane. So we did sort of like a north-south on one plane, east-west on another plane, kind of conventional routing stuff. And we've shown up to 3 planes of these waveguides with the ability to transition between them. Here, yeah.
Quick question. So, because if you have a single photon, you can't split a single photon, right?
That's yes. So what am I talking about here? What I mean is that when a neuron needs to communicate, say it's making 1,000 connections, it actually produces a pulse of light that has about 10,000 photons in it, and that factor of 10 overhead is for the propagation loss, which we assume is about 3 dB. That's relatively conservative, and also the shot noise, because you're not always going to split exactly as you would like. And so we calculate that if you produce 10 times more photons than synapses, you have a 99% chance of successful communication. Many people will argue that that's too much. In the brain, it's usually 70% or less efficacy, but we have 99% in this case. Yes.
And you're trying something that shoots at 10,000 photons to float?
No, so that's actually really dim. So a light source that you would usually use in telecommunications to go from one server to another in a data center is producing probably 1 billion photons for each pulse that it needs to send. And here we're actually producing maybe 10,000 to 100,000. So actually significantly dimmer. So Making it small is not that hard. These light sources are a couple microns, much bigger than like a transistor. Lithography is not a problem. The thing that is slightly challenging is to keep the capacitance as low as possible because we want to pulse these light sources. And if the capacitance is high, you end up spending all your energy bringing it up to voltage. But it's not that. But like I said, producing light is the dominant energy consuming step of all of this. And a lot of it goes into that capacitance, light source inefficiencies, propagation losses. Any work that can be done to bring all those efficiencies up matters at the system level.
When you say capacitance, there's no capacitance in the optical.
In the light source itself.
Yeah.
Yeah. Make sense?
What is the current level of efficiency for the generation?
Well, so we're working with some partners right now that make what are called VCSELs, vertical cavity surface emitting lasers. And the state of the art there is 70% efficiency. We haven't shown that in this system. We're actually working with them to get our first prototypes where we've bonded the VCSELs to these waveguides and cooled them down at low temperature. In our previous life, when we were at NIST, we made these light sources. Actually, I think I have. I guess I skipped those slides, but we made these light sources entirely out of silicon because silicon is a terrible light emitter at room temperature, but it's like only a pretty bad light emitter at low temperature. And so the best efficiency we got there was 10 to the minus 5, which isn't good enough in the long term. It's good enough for some near-term demos, but if you really want to get this to the efficiencies where you can build, our target is to make a trillion parameter model with less than a megawatt total system power efficiency. You need to get to 10 to the minus 4 light production efficiency, basically another order of magnitude better than we were able to get with silicon. And that's part of why we want to switch to conventional compound semiconductor light sources. Anyway, okay, so we showed that we can route light around with these waveguides. We can control the envelope so we can get light to different places. And we want to scale this up. We want to go to multiple planes of waveguides because we think about 10 planes is enough to get extremely dense interconnectivity across 300 millimeter wafers. We're not there yet. So now since we launched this company, our team came on board in January. We've taped out 2 chips and we're about to finish up the third one. We only have results from the first one. So I'll show you the first thing we made. It's just the superconducting electronics. There's no photonics in this. So the process is much simpler. And what we did, here's some examples, microscope images of our Josephson junctions, some of the computational cells that are doing the synaptic operations. And we built some small neural networks, sort of proof of concept, just to show that we can go beyond the device and sort of synapse level up to small neural networks. And so we built a feed-forward neural network that is in 2 different things. We did a 4-pixel bar detector. So just the smallest number of pixels you could possibly have where you're detecting horizontal or vertical bars. And we also more than doubled the size of the input to 9 pixels for an image classifier where you can tell the difference between the letters S, K, and Y. So this is sort of like the smallest level of MNIST you can possibly do. But the good thing is that this is our first chip. It has all these different networks on there. We're already able to classify images at 10 million frames per second, and that's limited by the peripheral measurement apparatus, not the chip itself. And it got perfect accuracy. It's not a hard task, but still, it did.
It's room temperature.
No, this is happening at 4 Kelvin. Yeah, all of this will always happen at 4 Kelvin. If anybody ever tells you, well, maybe one day you'll have room temperature superconductors, maybe, but it doesn't matter because these will always be at 4 Kelvin because room temperature superconductors are not conducive to manufacturing multiple planes of integrated electronics. It's never going to happen, in my opinion.
Plus, you want low thermal noise.
You also want low thermal noise. Yeah, that's absolutely true. Yes.
Naive question. What is the power consumption of the cryo relative to power consumption of the?
Well, it's all cooling it down. So basically, however much power your chip is dissipating, you multiply it by about 385. And that's the sort of common efficiency of a commercial cryostat that you can buy. So all of our energy estimates include a factor of at least 385. Sometimes we're just back of the envelope and we do 10 to the 3. We just multiply by 1,000. But that dominates everything. So when you build a trillion parameter model, the actual compute is using like 100 watts or something. But you have all this overhead just to keep it cold. And that's the only number you quote is just what does your cryostat pull from the wall?
Scale linearly or?
Pretty much, yeah. It's just Carnot efficiency. There's some Carnot is the fundamental limit, and then there's a factor of 2, 3 on top. Yeah, since you're asking about it, I'll diverge a little bit. When we're building towards this trillion parameter model, it will take up about this much space, like a meter and a half or so on a side. And so what cryostat can house that? Well, there's one called the Lindy L280. There's a company called Lindy that makes a lot of helium reliquefaction systems, and that retails for about $6 million. And so it ends up being about 30% of the price of the thing, and it uses 160 kilowatts. So 160 kilowatts is what it takes to power up a trillion parameter model made out of this hardware. Then you also have to get data in there. It turns out that the digital front end to just get as much data into the system as you need uses about as much power as the cryostat. So it ends up being about 320 kilowatts to power a trillion parameter, in this case, video analysis model. And compare that to the gigawatt data centers that Meta's building to do the same thing, we come out ahead by a fair, comfortable margin. Okay, so if you want to watch a movie, movies never work. Why? Okay, you don't want to watch a movie.
Yes, everyone.
Maybe you on laser mode.
Is that why?
Yes.
Oh, there it goes. Look. Okay, this is fantastic. So we can tell if so what you're showing here is if there's no bar detected, then you get a dot down here, and we're putting in all the different combinations of images. And when there's a horizontal bar either up here or down here, one of the output neurons gets active, and when there's a vertical bar either here or here, the other neuron gets active. So let's see. Let's see if we can watch it again.
Sorry, what is this?
This is just a video of the network doing its thing, just trying to demonstrate that it can happen. And for some reason, it works like okay, here we go. See if you can catch it. There, no, there. It's the lamest possible video you can do with a neural network demonstration, but it worked the first try. We taped this chip out within 3 months of founding the company, and so obviously we're working on more demos right now, but this is the first one that we had, so I thought I'd go ahead and share it. And so we're working on our third chip right now. The second one is in fabrication. The third one is, so here we have a few different variants that we're taping out on this wafer. This is just all-to-all connected 28 to 28 neurons, every neuron connected to every other in a crossbar array, plus 8 inputs that go to each of the 28 neurons. It's a total of 1,008 reprogrammable parameters that we can use to implement a bunch of different models. And then over on the right-hand side are some smaller networks that we're using to test various things, sort of like those 9-pixel things that I was just talking about. So this is what we're working on now. Still small scale, but we think this universally programmable 28 neuron accelerator will be kind of exciting, and we'll be able to do some things at a high speed and hopefully get some interest. Here's our roadmap over the long term. This is where we're at right now, where we're doing these 1,000 parameter accelerators, mostly looking at time series tasks. We want to build up to 100,000 parameter within probably less than 3 years. Hopefully we can do that. Actually, we think we might be able to get there in about a year because we're already taping out this chip right now. Then we go to multi-chip modules, wafer scale modules, where one wafer has 40 billion synaptic parameters on it, and it can perform 65 times more operations per second than a human brain. We think when we get there, this is going to really transform the way people think about AI. But you don't stop at a wafer. You can use optical communication to communicate between wafers that are stacked, and also fiber optics over longer distances, until we think 10 years from now, a lot of people are going to be really excited about programming models on hardware that is bound only by the limits of physics. So
in this model, you use one synapses for one neuron, or you have one neuron in many synapses?
One neuron in many synapses. The way that we sort of think about it is, as you scale up the chips, You want to keep the network average path length about constant to about 2.5 or so, between 2 and 3. And so what that means is that as you add more neurons, each of those neurons has more synapses so that the average path length stays in that ballpark. So it means that this scale of chip, you only need a few 10 maybe connections per neuron. Here you need more like 30. And by the time you get to over here, you're making 1,000 or more, maybe 10,000 connections per neuron. Each neuron makes 10,000 synaptic connections.
Each one, they have different
Different synaptic weights.
that mean different delays.
Yes, light speed limited delays, so they're very, very short. But yes, there you do need to take account of that once you get to several meters of a system. That's right.
Yeah, because the delay is important in the code.
Absolutely. Yes, absolutely. Yep. Yeah. Okay, well,
You'd have to hard code all of your synapses in. You don't get to change.
you can change them. So, okay, when you're at a system of this scale, it's impractical to have control lines going down to every synapse. You can do crossbars and things where you can address them individually, but you have so much more electronics going just to program the synaptic weights that the system becomes cumbersome and all your infrastructure is about programming and not actually computing. And so by the time we get here, actually, even already, we're working on local learning rules. We think the secret to overcoming all of the bottlenecks of, not all of them, but a lot of the bottlenecks of today's AI come from the fact that you're doing back propagation. And so you build a system, you train it once, you have to go deploy it as an inference engine, and then it can't learn anymore. And so that leads to a lot of problems. And it's also very inefficient because backpropagation requires non-local information. So you have to move things all over the network. We are looking for local learning rules, presumably a Hebbian learning rule with a reinforcement third factor that allows you to do something like the striatum does in biology to have a reinforcement learning rule. And that's how you train your excitatory synapses. And then your inhibitory synapses have a similar learning rule where it's Hebbian plus a decay factor that's just the local activity, and that achieves excitatory inhibitory balance. And we're looking at the ability to train large networks with those local learning rules, and we think that's very exciting and promising.
You have simulations showing that those local learning rules.
No, I want to hire somebody to work on that. Are you interested in it? Do you need a job?
From my take my job away.
Yeah.
I got one question in the back propagation. In this model, you use it back propagation inside of the circuits, or you use it outside
It's that. So what we've done to date to like train these other things that I was talking about, we do that all in simulation. So what we've done so far is we have I'll say a little bit more about our model of our circuits, but we have this model of the circuits. It's implemented in PyTorch, so we can use all the PyTorch framework to just design networks. And then we program in the synaptic weights that we got from a GPU simulation of our hardware. So it's cheating a little bit, but it's, whatever. You still come away with a chip that can work really fast. But that's how we're doing it right now. We have not physically implemented local learning rules yet. That's sort of like that's hard. It's not, there's a lot more basic research that needs to be done there. So we think as a company, we're not going to do exclusively that. We're going to continue to work on training networks with backpropagation, training networks with energy models, basically anything that you can do to make your network useful, we'll try it. But we think in the long term, to get to trillion parameter models that learn and think like humans and are truly performing the act of cognition, we think you need local learning rules with some kind of a basal ganglia type module that is doing like an actor critic type reinforcement learning model. We think that's essential to how humans become intelligent. There has to be some kind of a reinforcement learning aspect to it. Yeah.
Because plasticity may have to cool down over time. You don't want to constantly change, right?
Yeah, and so that's like a metaplasticity concept, and that's relatively straightforward to implement as well. You need another circuit applied to your circuit, but it can still be local, or it can have like a global neuromodulatory signal that comes in actually from like one of these bias currents. If you change the bias current to your plasticity circuit, you can make it very active to where the learning rate is high, or very low where the learning rate is low. All these things are possible. It's just a matter of wrangling the complexity into something manageable.
So, and at some point, you may want to freeze your network.
Absolutely.
Now, all of the synapses here, all the storage, right? It's volatile, I guess, right? You current in the loop and it stays there forever in principle.
Until you heat it up.
Right? Or you plug a cord.
Yeah, absolutely.
Right? So
Yes.
there's no volatile storage here. You have an electronic system.
It's a big challenge, that's for sure. There are things you can do to have non-volatile memory, but the dominant memory mechanism would require that this thing stays cold. That's true. Yes.
Or have some backup somewhere. There's electronic storage, non-volatile storage.
Well, how do you do that? I mean, it's possible. I wouldn't rule it out, but it becomes cumbersome because if you have all these synaptic storage loops, and now you need some backup where every one of those gets written to flash or something, that's a whole other layer of circuit complexity.
Sure, but you may want, let's say, again, eventually you have a product, you have a system, right?
Yes.
And it runs here in San Diego, another one
Yeah.
runs in San Francisco, right? You may want to port the parameters from one to
Yes,
the other.
yes, absolutely. That's the dream. That would be ideal. It's quite challenging, just like it's quite challenging. I would love to port what's in your mind into mine. Trust me, that would be very helpful. And I don't have a way to do it.
Can control it in the synapses. It's feeding these synapses. They have a own source of energy, right?
Yes,
And then you can control this energy in order to get some.
but that would require, even at arbitrarily large system scale, maintaining the ability to program every synaptic weight. And so I would need to take what's inside the learned brain at UCSD, map that into some, big database, and then go and program every single one of those into the one that's in San Francisco. And it's entirely physically possible. I just think it's really hard. And my intuition is that what you're going to do is they're going to diverge, and you're going to build one like sort of foundation model,
Yeah.
and then you're going to give that to UCSD, and it's going to become their computer. And 10 years later, after it's learned everything based on everything that they've put into it, it's a unique gem that is very difficult to reproduce somewhere else. And I think that problem persists, and that you have a fundamental trade-off, I think, in reality, where you can either be truly profoundly intelligent or reproducible and easily ported between two machines, but probably not both, because the ability to become that intelligent requires making decisions that you have to spend your circuit area on something. And if you're spending it on the ability to reprogram all the time, you're not spending it on the ability to have dense local intelligence. There are fundamental trade-offs it's just the way you're using space, ultimately, at the end of the day.
Building intelligent machines that have a life.
I kind of see it that way. And don't get me wrong, like, this is one trajectory. There is another trajectory, and this company might have to make some hard choices about what we focus on. And we could go another direction where we say everything is entirely programmable and everything can be ported between machines. We can absolutely do that. I'm just saying it won't be as smart as the one that was dedicated to a certain thing.
There's mechanisms of memory consolidation in our natural brains that can also help here.
Like hippocampus to neocortex during sleep, that kind of stuff. Yes, absolutely. Yes. And I also think that over time, UCSD gets their massive supercomputer. I'll write up the purchase order. You guys can make a purchase. And then you guys will train it over the course of several years, and you'll learn a ton about how you wish the architecture was different. And that'll go into the next product generation, and its foundation model will incorporate all of that consolidation that you guys figured out, and it will become smarter. And so evolution over longer timescales will happen by those kinds of iterations, just like generations of living organisms. Yes.
So this is fascinating, and I'm not a neural computational person in any sense, but one of the biggest problems that we have in large scale computing is reliability.
Yeah.
And so what is the story here that you just have such an overabundance of connectivity and such a surplus of computational elements that the thing is just going to decay in place and learn around its faulty components?
I mean, yeah, so then you can point to the arguments of parallelism and redundancy in biological neural networks. So yes, you build sort of like an overcomplete network that has more connections than it needs, and some of them turn off over time because they're not being used. And if anything breaks, there's another way that information can be routed to overcome that. But I will also say that this hardware is kind of inherently reliable. Besides the thing that Gert pointed out about you unplug it and then it loses a lot of its memory, unfortunate to be sure. But for example, like the synaptic weight mechanism, the storage is just current going through a wire, and it's a relatively low amount of current going through a superconducting wire. So there's no like electromigration or anything. There's no degradation of metal semiconductor contacts. All of the failure analysis mechanisms of semiconductors, I shouldn't say all of them, a lot of those mechanisms have to do with the fact that they're heated up, they're at high power, high currents going through them, and relatively high voltages. These are very low sub-millivolt signals, 100 microamps of current without the electron wind that drives ions to electromigration. So you don't have, and you don't have metal semiconductor contacts, or you only have them at the light sources. And those light sources are typically rated for uh, being driven in a data center at 100 Celsius for 10 years. And now we're cooling them down, driving them at 100 megahertz pulse rate instead of 10 gigahertz. So, and we're driving much less current through them because we're trying to get less light out. So everything about the reliability is more favorable in this case. What's more likely is that you build a system, the hardware doesn't degrade over 10 years, but you want the next generation. And that's why you end up, it's not planned obsolescence, but the system does become obsolete over time because we learn so much about how to make them better. Yeah, see, there was a question here. Carlos, go ahead. Oh, wait, sorry, if you were talking, start over. I don't hear it. I don't know if it's on.
It's like that's
Carlos, say something?
You know,
Carlos, you have a question?
Maybe you can type it.
I
All right, while he's typing that, I want to cover one more quick thing. I was going to talk about this a lot, but I got a little sidetracked, I guess. So I want to explain our modeling framework because it's really kind of convenient, and I hope people will want to participate in this. So basically, if this is the circuit we need to model, this is sort of a dendrite, and these are the synapses coming in. This is the core computational primitive. If you can model this, you can basically model everything in our hardware. And it obeys this very simple leaky integrator equation. So gamma is just some growth rate that you can choose in hardware. Tau is a decay rate. S is the signal. So you can think of S as the activation of a neuron or of a dendrite if you're thinking about active dendrites. And then so all of the magic of the model is in this function G. This is your nonlinear source function, and it looks like this. So the phi is the input coming into a dendrite. So as you go along the phi axis, you reach a threshold and then you kind of go up monotonically and then it rolls over. And then as you accumulate more signal in the dendrite, you're coming down these traces and you reach a steady state in this plane where G actually, this is the dendritic source function equals 0. So all of this is really easy to model in this framework that looks pretty familiar to most neuroscientists. Yeah.
what is the dendrite? It's a fiber optics. It's a fiber.
No, it's this superconducting electronic circuit. So this is a dendrite. This is the active part that
Optic with the synapses.
it can either take in synaptic input or input from other dendrites. Either way. It's just like a dendrite in your brain. You can think of this. Yeah, go ahead.
Carlos has.
Okay, okay. So let's see where. Okay, let's just see it there. So I don't want to switch away from this because I'll never be able to get back.
So, present tech, how does the architecture implement parallel computing? How many neurons can be theoretically used simultaneously? Can they actually go synchronously against something?
Yeah. Okay. How do we implement parallel computing? Natively, that's what this does. All of these neurons, dendrite, synapses, they're all just active on their own. They don't care what the other ones are doing. They have completely independent power supplies, completely independent inputs and outputs. So it is inherently an asynchronous computer architecture. How many neurons can operate simultaneously? The answer is however many you built on your chip. Right now, we're at something like 28, and we need to get to 10 trillion as soon as possible. And those will all be able to, in principle, operate simultaneously. They shouldn't because that's a horrible epileptic seizure, but in principle, they can. And sorry, there was a third part there.
Synchronous.
It's all asynchronous. There's no global clock here. The neurons in these networks develop their own oscillatory behavior, just like neurons in the brain. You have nested oscillations between gamma and theta. And as I said before, everything's just accelerated by a factor of a million. Global oscillations at about 4 to 8 megahertz with nested gamma oscillations underneath up to 100 megahertz.
Okay, question from remotely.
Yeah.
How do I seem to have missed the part where you tweak the connection strength between all these neurons.
Yeah, so tweaking the connection strength between the neurons so we've shown, for example, here is where you can change the amplitude of a postsynaptic current in this case by putting in little pulses that program this circuit right here. So you can increase or decrease the synaptic weight by putting in little programming pulses, or you can do it with local learning rules that potentiate or depress the synapse just based on sort of like Hebbian or three-factor activity. And then what I'll show in the modeling framework, the way that this happens is you have so this is our model. Every single neuron dendrite in the system has its own local S signal. We call it the signal, and it is evolving in time like this, and it's being driven by its input phi. Oops, let me see. So this is phi. So phi is just a linear summation of the inputs there, which is kind of just the simplest thing you can do. You linearly sum the inputs, and then they enter the nonlinear aspect of the transfer function. So it's the Jij that change to implement the synaptic weights, and those are implemented by that synaptic weighting circuit I just showed a second ago. You literally multiply the synaptic weight by the input to the synapse.
So you program them by giving pulses that either ramp up or depress the weight.
In a supervised learning paradigm, that's exactly right. Yes.
Okay, I mean, I can see how you do that for 28 neurons, but I can't see how you can do this for trillions of neurons.
I agree with you, and that's why we think we need to move to local learning rules where you don't do it. The learning rule says if the presynaptic neuron is active and the postsynaptic neuron is active, and I'm getting this third factor that says now's a good time to learn, then you increase the synaptic weight. Or if you say this one is active and this one is active and your error is really high, then decrease the synaptic weight. Those are the kind of learning rules that we think are necessary to get this to scale to many trillions of parameters. And I don't think that's specific to us. I think that really goes for any lifelong learning system, regardless of the hardware. If you retain the ability to reprogram every synaptic weight, I contend that you have given up a lot of the ability to make that system more intelligent, simply because you're using space and using resources for programming, and you as an individual were incapable of giving up your control over your child, and you need to let go.
Okay, yeah. I mean, I asked the question because all these trillions of neuron systems run into that problem some way or another. Yes.
Yeah. I think it's sort of like the very heart of the problems we need to solve as a sort of neuromorphic community. Um, well, okay, so this is how you model. I'll stop there. I'm at the end of time. The final point I'll make is that what?
Keep going.
Keep going. Okay, so this is how you model a dendrite or a synapse. It obeys exactly this equation. All right, thank you. Appreciate it. Then if you say, well, I also want to be able to model spiking neurons, that's annoying because you have these spike discontinuities. And so a spiking neuron signal might look like this. Here's a kind of elaborate, messy schematic of what that neuron is, where the transmitter is producing these little pulses of light. And then the postsynaptic signal is this sort of long pass filtered version of it. But what we would like, so when you go back to a dendrite, actually, if you follow the exact circuit equations, it's kind of rippled like this, and you have to zoom in really close to see it. But this phenomenological model, so this is a phenomenological model. The real circuit equations look like this. So phenomenological model dashed green, real circuit equations, this wavy black line. We do not want to have to address all those circuit equations. And so that's why we came up with the phenomenological model that ends up being 10,000 times faster, but still accurate to 1 part in 10,000. So 10 to the minus 4 level accuracy. And you can see on this time scale, I'm zoomed into a picosecond time scale window. It's like 150 picoseconds. You have to zoom in to see the difference. Now, what we want to do is do something similar for spiking.
I just want to.
Yeah.
Didn't mean to derail you.
That's okay.
Where do the steps come from?
They come from the specific dynamics of these Josephson junctions. The Josephson junctions, in order to produce a voltage, they need a discrete phase shift of the superconducting wave function around the loop, and that just brings a little temporary blip. So
Is that a quantization?
it is a quantization effect, yes. And so
This station is dependent of the peak of the photons.
it has nothing to do with photons. It's just about the superconducting electronics. It's in the Josephson circuits. So it's built into the physics of how this the fact that basically what it comes down to is that you have one superconducting wave function around this loop. It's all superconducting. And that needs to be an integer times 2 pi. So it'll make a 2 pi phase shift, and that releases exactly one flux quantum, and that's the quantization, and that leads to these little steps, but they don't matter. And the reason they don't matter is because you always low pass filter the output. If you didn't, then they would matter, but you always low pass at least something like those pulses come on a picosecond time scale. You're always trying to integrate at least 10 picoseconds, usually much, much longer.
Maybe take advantage of this quantization in some application.
You absolutely. So a lot of other people said, those are our spikes. That's our neuron. And you can build entire neurons that go, I said ours go up to 100 megahertz. They could go up to 100 gigahertz.
A stable memory because it's one of the quantized states.
And that's how our memory works too. I call it sort of like an analog memory, but it's actually discrete levels. They're just very closely spaced.
Can control this quantization.
Yes, you
control by the geometry of the sequence.
That's true. You can control it, but it doesn't matter very much. And so my perspective is don't worry about it. Instead, we want a spiking model that looks where you have a phenomenological version of it that when I first set out to build this model, I was like, I would be satisfied if it looked like this. And so we said, okay, without going into all the details, what if we do we just say our neuron obeys the exact same equation of motion, this equation here, but we're going to look for a different source function. And we just numerically simulate it and do some fitting until you find some source function. And then when we found that actually it can, so now I'm showing this is the information coming from single photon events. That's like the postsynaptic signal. And then it goes into a dendrite here, and that feeds into a neuron. And we're saying this dashed green line is supposed to match the black line, but it's this phenomenological model where it's all completely continuous, differentiable. You don't have to worry about spike discontinuities. And the model still tracks the spike discontinuities pretty well. And then, so in this dash box, I'm zooming into that over here. You have to zoom in pretty closely to see that the low pass filtering is actually kind of rounding things out. So it's not a perfect model, but if you're trying to simulate a trillion parameter system, you don't get a perfect model. You have to, like, if you're a computational neuroscientist, you're not solving Hodgkin-Huxley to understand how the hippocampus works, or at least not once you get above a certain scale. So it's the same basic thing here. So we have this phenomenological model where you ignore all the spiking that happens, and it just all gets summed into this input and then driven to these downstream dendrites, and it just has a slightly different source function. So here's G for the dendrite, here's G for the neuron, and we have one model that simulates all this stuff across different spatial and temporal scales for every component in the network. Neurons and dendrites obey the same equation of motion, which makes it really easy to implement in PyTorch. So we've built all this stuff in PyTorch. And then one of the most important things is, okay, well, what's the steady state behavior? You're going to want to know, if I'm putting in some input and then I hold it fixed, what does the network settle to? And you find that it all falls out of the source function. That's the projection of the source function where it meets the S phi plane, and it looks like this. It's a rectified linear unit. Well, it's rectified linear-ish unless you have a high leak rate, and then it kind of rolls over and looks more sigmoidal. And so that's for the dendrite. And then
Does it have sigmoidal?
when you put a high leak rate on it.
Okay.
So when the time constant is on the order of the interspike interval, basically.
All right.
And in this case, like you can see there, it's like 10 nanoseconds-ish. So if you had a leak, like I've been saying, the gamma frequency is 100 megahertz, which is a 10 nanosecond interspike interval. That's the highest gamma frequency. So if your leak rate is on the order of the interspike interval, you get a rollover like that. And then, and so our dendrites have a steady state transfer function that's ubiquitous in ANNs. This is very useful for building artificial neural networks. And then our neurons, they actually are kind of interesting as well. So this is the projection in the S phi plane, and they have this very sharp threshold. However, turn on a little bit of thermal noise, which is not in these simulations, and that's going to roll up like this, and it looks like a sigmoid linear transfer function, which is another ubiquitous transfer function in artificial neural networks. So we have these building blocks that allow us to do a bunch of stuff that is really fun in the world. So, okay, those are the points I think I wanted to make. This is it. This is the whole model. You can implement this, you can simulate everything, and now it's just a matter of making this computationally efficient. So we've done a lot of stuff trying to parallelize this, farm it out on GPUs, and it seems pretty tractable, although as a company, we have not attempted to go beyond 100 million parameter models, and that's where we really want to go. We want to get beyond billion parameter models during this seed round that we're in right now.
How you know that this is realistic, this using these equations?
How do we know that okay, so well, so actually we know numerically it's realistic. So, okay, so here's an example. This is the simplest example. I have a whole paper about this. I think this is the reference there. This shows comparison between the dendrite model and the exact circuit equations. And we find that under almost all circumstances, it's accurate to 10 to the minus 4, comparing numerical circuit equations to numerical phenomenological model. And this is what you see. So if you just put in a step function of input drive here, then you see that this ramps up. And so on this zoomed out time scale, they fall exactly on top of each other. If your model is sensitive to those kinds of differences, you need to consider a different model. I mean, a different architecture or something. But you have to zoom into this tiny box to see the difference. So numerically, we can confirm that it's highly accurate. But then in circuits, we've built these and we've shown that the image classifier works. And that's kind of it's the difference between the circuit we build and the circuit we designed due to fabrication imperfections is far larger than the difference between the circuit that we designed with the phenomenological model versus what we would have designed with the exact circuit equations. That is a very close agreement. And then when you go and make something, as any circuit designer knows, especially if you're doing analog, it doesn't come out exactly as you designed. So that's the real discrepancy.
Morning, good.
Yes, exactly. You can compensate.
So to understand this is that you have a step function of flux of phi,
Yeah.
then into the circuit, and then the system integrates over time.
That's what's happening in this particular instance here. Yes.
Then because it's superconducting, there's some integer wavelength, I guess, so waveform, is that it? That
Yeah, you can say it like that.
that sort of it, and so as you integrate, you change energy level, sort of similar. And then you basically change to integer, and so therefore that's where this discretization that we see is that.
That's right. This discretization comes from the fact that the superconducting wave function in this loop is quantized into, it has to be an integer of 2 pi. But I would encourage you not to care about that. I don't think it matters.
It is important because this ensures that you keep your memory, you keep the state forever.
Well, so there's two different things here. One is this is the active leaky dendrite. So it's going to integrate some signal on what the analog of the current on the membrane in a biological case, which that's also quantized too, right? There's only an integer number of ions that can be across that membrane, but it doesn't matter because you have such a large number of them that it smears out. And then it leaks also. So if it's leaking in time, you maybe had an integer number, but it's time continuous leaking and you end up in some perfectly analog value. That's in the active dendrite. Don't be confused between that and the synaptic weight that stores a memory, and there it's discrete and you don't have a leak, and there it sort of does matter that it's discrete. But again, if you go to 8-bit, you have 256 levels. They're pretty close to each other, and you don't need to bother yourself with, wait, was I at level 231 or 232? Like, it shouldn't matter very much.
It doesn't matter as an engineer ensuring that it doesn't decay over time because this is a quantization mechanism that ensures.
That's true. Yes, that's true. That's what makes it non-volatile in the sense of it will stay there forever as long as it stays cold. It's volatile in the sense that you pointed out, where if you unplug it from the wall or some nefarious entity comes into your lab and unplugs it, then it's bad news.
What about the axon?
What about the axon? Okay, so the axon, that's the photonics. That's the part, that's this. So that's where you have, this is the axon. And it's a branching, so light gets coupled into a waveguide. That's a simple material made out of basically glass on an integrated circuit. The same insulator materials that are used in fabrication today, silicon nitride.
They arrive with the dendrites. The dendrites have electrons, right?
Yeah.
And then you need to translate, convert
the transduction. Yes, that's this circuit here. So sorry, I got on my screen, there's this thing in my way. But so with this circuit here, a photon comes in, it hits a single photon detector. This is an absorbing element, and it's not, the photon doesn't propagate through it. I mean, there is some minor reflection right where it hits that, but it's a very, very low impedance change. So then it gets absorbed in that material, and then there's no, then it couples its signal into the electronic device here. This is the dendrite. And now you've transduced from a single photon optical signal.
So what is the frequency? No, for all frequencies happening.
It's monochromatic. The light is just one wavelength of light. You produce a pulse of light that is.
No, but the coupling in the superconductor is not in all the frequencies. It's only one.
So I believe you're picturing a microwave signal coming into a superconductor.
That's it. Frequency. Is it infrared or is
it's infrared? It's near infrared. It's telecommunications, somewhere between around a micron wavelength. And it just gets absorbed. It's propagating through this waveguide. It makes sense?
Yeah, way this absorb these photons and they convert the energy into the electrons. Right?
Yeah, that's right. They convert energy into the electrons here. That produces a resistance and it kicks current over here. But the impedance, so I guess I don't have a great picture of this, but like the light is propagating through a waveguide, and then the detector is just a metal strip on top of that waveguide. The evanescent field of the photon experiences that metal strip, but the overall impedance change that the photon experiences is very small. The reflection coefficient can be less than a percent. So it's not a big problem to impedance match in this particular case. It's very different than microwaves going through coplanar waveguides.
But you know that is proportional in this in the meaning that here you have very few electrons. They're not that very few changes in the coupling. They change a lot in the electrons because you have very few electrons, very few photons arrive. The coupling is very few, and the electrons are very
So
few.
it works better than you think. And so the reason is because these superconducting single photon detectors are almost miraculous devices. If you picture the nanowire, this is a superconducting nanowire single photon detector. It is a strip of superconducting material that has a superconducting wave function through it. That means a bunch of Cooper pairs. The superconducting gap there is on the order of, hold on, milli-electron volts. So, something on the order of a few milli-electron volts. And so the energy of the photon is on the order of an electron. It's about an electron volt. So now what happens is the photon comes in, and the initial thing that happens, we think, the microscopic physics here is still not entirely resolved, but one Cooper pair is broken. And now you had one really hot electron hole pair. And that within, on the order of a couple picoseconds, there's a thermal cascade where that really hot electron makes many thousands of electrons hotter and breaks superconductivity across the entire width of the wire. That's what's called a hotspot. So now you went from a superconducting wire that has exactly zero resistance to something that has a kiloohm because the whole width of the wire went normal, and it's about a kiloohm per square, and it's about one square of wire that became normal. And a kiloohm is more than enough to kick all of the current out of this into the other branch of the circuit in about a few picoseconds. It's a few picosecond rise time. And then the return time is set by this L over R time constant, which is, it needs to be about 10 nanoseconds or longer. Otherwise, this doesn't cool back down. So this is what's called in this field hotspot dynamics. And it's an active area of research, but if you just want to have rules of thumb, it works every time. Like one photon comes in, makes this hotspot, you kick out all the current, and it comes back in 10 nanoseconds. Great. That's enough for our company to go make these all the way into the future.
So does that photons basically dies there, gets absorbed, energy gets absorbed? Do you have systems where the other photons keep going to connect with other dendrites?
So yeah, what you have is a pulse of light, and you want to route it roughly evenly to all the downstream, not roughly, you want it to be as even as possible to all the downstream synaptic connections. But they have different terminal waveguides. So you never pass through a photon and go to the other side. You make this detector as close to 100% absorbing as possible. And then there's other axonal branches that go elsewhere.
So also in your figure of the axons, you have these things in the middle that are not being touched. Is it simply that there's a wave of, okay, what are in the top and bottom? What are we seeing in the middle?
It's other waveguides that can branch to and go to different destinations.
That from somewhere else?
No, this is one source going. So the light is coming down.
The one on the right.
The one on the right, you mean over here? So, okay, what I'm showing in this picture is this middle one is 3 planes of waveguides.
Yeah.
This panel is the top green waveguides. This middle is this image is the blue middle plane, and this one is the lower yellow plane. So it's all the same thing, just like you're taking different cross sections.
But it's not like the middle one suddenly get the same signal, or does it?
That you have one pulse of light that has on the order of whatever it is, 1,000,000 photons in it, and you're branching it with certain ratios at each of these beam taps. We call them.
Stay in the waveguide.
They go into different waveguides.
Here they look like they're jumping.
They do. It's an evanescent coupling phenomenon. And what that means is a photon is a wave, right?
Yeah.
So
So they jump.
They jump through an insulator.
Superposition.
Yeah, it's kind of like a tunneling effect.
Wow. So this one.
Yeah, it wouldn't. Yeah,
So it is what it looks like.
it is what it looks like. Yeah, the universe is amazing. Yeah.
Yeah.
So that also is quite an amazing thing because you don't have to worry about being so precise or finite, I guess, to some extent for your photon for your conduit for your photon to follow the conduit.
No, you don't have to be that precise. It's
No, there is something, now going back to biology. So in biology, axons have a regenerative mechanism. They're on the way they will.
nodes of reindeer or whatever.
Yes.
Yeah.
So here, I mean, you have a number of photons that start from, I guess, the source neuron. And that's all you have, right? They get distributed.
Well, you can do repeatering. There's no reason why you can't have
But
Oh, so
you're
you're
moving
not
with the speed of
going to-
light, not to overcome speed of diffusion, which is what the problem with the moves around the sun.
and the other thing that I'll point out is that the way that axons in the brain are able to pull that off is they're immersed in extracellular medium, and there's a voltage difference between the inside of the axon and the outside, and it's incredible nano machinery that allows that voltage to be maintained. And in any kind of artificial hardware, it requires an external wire coming in, and you're dissipating power all the time, and so I think if you can do it passively, it's actually better.
Sure. But at the end of the day, if you want to fan out of, say, 10,000 or whatever.
Yeah.
And just the way it venture trillions of waves, this means you either have billions or, right, of those structures.
You do. It's like the axons in your brain. From every neuron, there is a dedicated path that goes to every synapse. You go along an axon and then it branches, and then you follow that and then it branches. You have to do the same thing.
This may be the bulk of all of the.
Yeah, so that means I think your question is, what's the ratio of gray matter to white matter? Yes, and I think the answer is my understanding is that in biological systems it follows a power law and the exponent is about 1.4. And in this system, I don't know what the exponent is, but it's going to be a power law also. And so for small systems, it's gray matter dominated. But as you get to larger systems, it's set by the diameter of a fiber optic patch cord, because you get over to, you end up being on this picture here. And this picture is actually a really simplified version. Instead, what you would end up having is a massive fiber bundle contacting every top wafer in a column. These are supposed to be cortical columns. And so you have like 1 million fibers going in, and then those go out to different places and you do different attach to get where they're going. But the diameter of those fibers sets the exponent in the gray to white matter ratio. And I believe that it ends up being around 1.4 also, but I'm not too confident in that.
It should be scalable.
Yeah, but it does end up being the limit. Why can't you make this the size of planet Earth? That's why.
As long as the average fan in and fan out is constant, it should scale and it should have a certain ratio.
Like a Rentian kind of scaling. But the problem is that when you get to really large systems, even if it's like a Rentian scaling where the number of connections into a volume of space is a power law of the number of nodes within that volume, you get to where at a certain point, if that exponent is less than 1, which it always has to be, otherwise you get too much white matter. Things get so separated that they become essentially isolated computational systems, and they can't efficiently exchange information.
There is very sparse global connectivity.
That's right, yeah. But you can still do it. That's true, you can, yeah.
Can you imagine, like, you don't necessarily need, the photons don't need to have waveguide, right?
Well, they can go through free space, yeah.
They could go through free space.
The problem is routing them, because they go through in a straight line. And if you want to pick off this photon and make it go over there, but let that one go straight and then let this one go that way, you have mirrors and stuff everywhere, and it ends up being I believe, even huger mess than fiber optics. But you're right, it is a smaller cross section.
And then it is not possible to divide.
It becomes very difficult to divide and route. Yes.
No, but if you have a sphere, right, then where you have all these connecting, they could still jump and go.
It's possible. I find when I try to play that out in my head, it becomes.
What's the probability of 2 photons colliding with each other?
Well, they can collide. They'll pass right through each other because they're bosons, but
It's a beautiful setup.
it could be, but I think it ends up being really hard to control where things go. And you don't want sort of random connectivity. You really want to control this bundle of axons is going from the hippocampus to the neocortex, and it needs to deliver right to that spot. And like, You can't do that with free space as far as I can tell.
But the thing is that you don't have the problems with electronics, because if they, where you have to have a wire going over the other, they can just cross each other.
That's
And
true.
so
You
in
do
some
have
places,
crossing.
you can save space.
That's true. In some places you can. I think that's right.
Therefore, this by itself suggests that you should have something much better than in the brain.
But then you have the problems in the coupling between the synapses.
Well,
the synapses, they are circuits.
yeah.
In superconductor, and they're greatly rated.
But I think what you're getting at is that you could have a bundle of fibers going this way and a bundle of fibers going orthogonal, and then let them couple into free space, and they can cross over each other and then couple back into fibers on the other side or something like that. And in that place, you save like factor 2 volume or something. Yeah, I think that's probably true. Yes. Those aren't the problems that Great Sky is facing right now, but
No, but it's sky's the limit.
yeah. Okay.
You know what? And this segues beautifully in next week's Chalk Talk
Okay.
by Eugene Zikovich.
Oh, really?
Because in a way, the message may be a bit complementary.
Mm-hmm.
Because when Eugene will talk, it will all be about spike timing, right?
Yeah. Yeah.
And I think here he's saying, so you have some systems where you don't care about individual spike timing. You have this average or this great mechanism.
Well, I care about spike timing to an extent, but I don't want to always have to model. If you computationally have to keep track of the time of all these spikes, it becomes cumbersome.
So you mentioned that in all practical cases that you studied, right, that you found that there's no difference. You can't tell the difference between the mean rate model, right, and the spike detail model. But this changes when there's coincidences.
No, absolutely, absolutely. And so actually in the paper where what I mean to say is not that you can't tell the difference. What I mean, okay, so in this particular model, the reason why we have access to a slightly different thing.
Well, this is this more talking about individual spikes accumulate. Oh, okay. Let me find it. Yes. I see it on the right side.
On the right side. Okay, so if you have a leaky integrate and fire model, say this is the model that you want to work with, or the Zikovich neuron, then you're in a situation where when the neuron produces a spike, it resets the membrane potential. That's the typical way that the leaky integrate and fire works. And so now you often are keeping track of those spike times, and that's considered the dominant mechanism of information communication. In this particular framework, which I'm not saying is the be all end all of anything, it's just a convenient way that we can model some systems. We have something different, which is that all of these signals that are coming into the neuron cell body here, you can say the membrane potential of the soma in our circuits, it doesn't reset when the neuron fires. It doesn't have to. There's no reason why it should. And so we have a time continuous signal. All of the states of all these dendrites and the neuron cell body, they persist before and after spiking. And that gives us a time continuous signal that we can use to build this phenomenological model so that it doesn't have to keep track of spikes if you don't want to.
Sure, in the mean rate.
But it's not a mean rate. That's the thing, is that there's no aspect of this that says that it's mean rate. And that's why I wanted to make this plot, is because
Sure it does, right? Because if all the spikes would coincide, let's say you have 100 spike all come in one time slice.
Yeah.
It will definitely be different from spreading them out.
Yeah, so okay, well, first of all, let me point to this plot a little bit more carefully. And these are individual spikes coming in, and the phenomenological model that has no notion of the rate of spikes is keeping track of individual spikes pretty well by just keeping track of the membrane potential and using that to drive downstream dendrites, basically. So you haven't said anything about rates or anything. It's just you're keeping track of this neuron's membrane potential and using that to tell you how much signal you're accumulating in downstream dendrites. However, when you do have coincidences, something weird happens. Let me see. I want to, let's see if I can, what is it? So here's this paper that I wrote about it. I need to share something else. So
So there's a difference also is that with the leaking Lagrange fire is that you have dendrites that may have their own dynamics, and then you have the neuron that has its own dynamics. And like in a biological neuron, the membrane may reset, the voltage may reset, but the dendrites dynamics stays on. And so you may have an effect after the reset of the membrane of the neuron that is due to the dendrites that have been activated previously.
Yes, I think that's right. And so sorry, I need to.
They're leaking, then they go down in this.
Well, they don't need to just be leaking, they can have dynamics.
They can,
dendrite
yeah.
itself can have dynamics.
Okay, so I wanted to look at exactly the thing that Gert was asking about, where you have this. Do you see this? Yeah. Okay. So yeah. Let me scroll down to the part that I care about, and then. So here's like responding to individual spikes. There's some different trains and stuff. Basically, what it comes down to is it responds pretty well as long as the low pass filtering on the other side is like, reasonably present. And so this is exactly this, where you have coincidence detection. So the solid lines are the spiking model. And what you find is that it's discrete, right? So like if the two synapse events on two different synapses came into the neuron within a sufficiently close time window that the neuron made a spike, then the downstream synapse accumulates something. And then the dashed lines are this phenomenological model. And you can see they're basically what you'd get from the spike model if you added stochasticity. So they're the average behavior of if you had stochasticity on the arrival times.
It's like so mean rate, it's a very accurate model when there's noise.
Yeah, and so
you're operating at 4 Kelvin, so the noise is very.
Well, it depends. This is not thermal noise. This is timing jitter of spike times. And that is not necessarily related to thermal noise in our particular case. It's not.
The physiological model would have a slightly different response delay, right? Latency. Like the curve, you may not reach threshold until later.
In the model, it's pretty close to matching the rise of the signal. So it's kind of funny because every time I present this model, like people have trouble understanding, like, is it a rate coding model? Sort of, but not really. The source term G is the rate at which signal is accumulating in the dendrite. Or if you're talking about the neuron model, it's the rate at which a downstream dendrite is accumulating signal due to the membrane potential of an upstream neuron. That's different than the rate at which the neuron is firing. This model is accurate even between spikes. It is a somewhat time average model, but it's not the usual rate coding model. I think that's the point I want to make.
I have a question. I think I'm like the youngest person here, but how do I get into this line of work?
Are you looking for a job?
Well, I'm like studying just computer science and biology, so I have a very surface level, coming into this. I like can understand half this, right? Like not all of it, but like what did you say? How do I like pursue this?
You got to come work for our company. Yeah. Oh yeah. So that was I was gonna say.
Yeah, if you got from the list or from the email that got sent out, I probably have his email.
Oh,
It's
yeah.
jeff@greatsky.ai.
That's
But you got to study probably like, it depends. You can just study the computational neuroscience side of things and go get into this at a sort of like abstract level, or you can go into the devices, electrical engineering. I personally studied physics. I think Gert studied electrical engineering, but physics too. Yeah. So you can do both. Yeah. Yeah. You can do both serially. Yeah.
I'm only an undergrad, right? So
Okay.
I think after that.
Well, yeah, getting a good internship is going to
For sure. Yeah. Yeah.
Well, where are you based?
Boulder, Colorado. Yeah. Oh, really? What brought you? Oh, cool. Yeah. Just on highway.
One goes from the national standards.
Well, that's where we came from. We came from NIST. So
Oh,
that's,
you came from that. I think you came from biology.
we came from NIST Boulder.
So there's one in DC.
There's one in Gaithersburg, Maryland, but it's not biology. Yeah, they do all kinds of stuff there. That's sort of the mothership. Yeah.
Steve says thank you.
You're you're thinking very pragmatic way. There you build the circuits, and then you have the results of the circuits.
Sorry, can
Yeah, you build the dendrites and the